Today we'll be using Gauss's law to find the electric field outside of an infinite line of charge. Let's start by setting up the problem. We'll start with this infinite line of charge. We'll just draw a straight line here. And we'll say that for Gauss's law, we usually want to exploit the symmetry of the problem. An infinite line of charge will have an electric field that moves out radially in all directions from this line. In that case, we want to use a cylindrical Gaussian surface, which we'll draw in. And we'll use this surface to exploit the symmetry of the electric field coming off the line of charge. The line of charge, we'll say that it has uniform charge density lambda, and we'll say that our Gaussian surface has length L and radius S. Now we'll also use Gauss's law in its integral form, which says that the electric field dotted with the infinitesimal area vector is equal to the enclosed charge over epsilon naught. And using this equation and this setup, we'll be able to find the electric field outside the infinite line of charge. Let's start with the left side of this equation. So we know that the electric field is going to be radial in all directions coming off this infinite line of charge. And the infinitesimal area vector of a cylinder is also going to be coming off radial in all directions away from the cylinder. In that case, our electric field is parallel to our infinitesimal area vector. This simplifies the dot product because E dot dA is going to equal the magnitude of E times the magnitude of dA. And this will allow the integral to become the magnitude of E times the magnitude of dA is equal to the enclosed charge over epsilon naught. And then we also can further simplify by noticing that the electric field is coming off radially in all directions from this infinite line of charge, but it will have the same magnitude at all places on this Gaussian surface if the Gaussian surface is centered on the line of charge. This allows us to pull the magnitude out of the integral. And we can go one step further and solve this integral just by finding the surface area of a cylinder, which is 2 pi times S, which is the radius, times the length L, is equal to the enclosed charge over epsilon naught. To finish up this problem, let's look at the right-hand side of the equation. So we want to find the enclosed charge by our Gaussian surface. So we find that by saying that Q enclosed is equal to the integral of our charge density, lambda, along the length of our Gaussian cylinder. We'll call that dl, and we'll break it up into small steps, dl. So we have said at the beginning of the video that our charge density is uniform, so we can pull lambda out of the integral, and then we just have the integral of dl. And if we integrate along the entire length of this Gaussian cylinder, the integral is just going to be L. So our enclosed charge is going to be lambda, the charge density, times the length of the Gaussian cylinder. So we can continue through. And say that the electric field times the infinitesimal area is equal to the enclosed charge over epsilon naught. And now it's just algebra to work through. We can cancel the length of the Gaussian cylinder on either side. And we find that the electric field magnitude is equal to lambda over 2 pi epsilon naught. And then we have this 1 over S factor, how the electric field is going to die off away from the infinite line of charge. So we, at the beginning of the video, said that the electric field is going to be radial in all directions. So we find the final electric field is lambda over 2 pi epsilon naught, 1 over S, and then our radial unit vector S hat. And one interesting thing to note is that the L's canceled on either side. So that means that the length of our Gaussian surface that we chose doesn't matter for the problem, and the infinite line of charge is going to have this electric field.